So we were working on volumes by slicing and volumes by the disk method. We have not yet started the washer method, but I have a problem I would like you guys to start with today. All right, so this is the example. This will be number 4, I believe. I'm feeling like it should be number 5, but do I have 2 number 2s? No, number 1, number 2, number 3. Okay, that's what I thought. This was number 4. Okay, and then this is number 5. And so I want you, so I'm going to put you in breakout rooms. No, actually, I'm just going to let you work on it and then we'll talk about it. So why don't we go ahead and work on this? So before we get started, anybody want to tell me something about the curve y is equal to x minus x squared? Any information you want to give me to help the rest of your classmates graph that curve?
It's a quadratic function.
Okay, so it is a quadratic function. Good. That is the most important thing. It is x minus x squared. So it is a quadratic function. Okay, so what does that mean? What shape does it have?
It makes a parabola or a curve, like a hill, like.
Okay, it is a parabola or a hill. So is it like this? Or is it like that?
The second one, because it's negative, I guess.
Okay, so that's perfect. So it is definitely going to be this one because it is y is equal to the negative x squared plus x. So the negative at 1, which is our a, makes it say that it is upside down, or well, yeah. So it is facing down. Okay, so good. Anything else you want to tell me about it to help us draw this thing? This is actually a rather easy problem. Okay, anybody else want to give any other information about how to graph it? When you're graphing a quadratic, when you're graphing a function, and you kind of have an idea of what it looks like, what are 2 really important things that help you put your curve on the graph?
Would there be points?
Okay, so if I could find some points. So what points are real important?
Y-intercept.
Good. Okay, so the y-intercept, excellent. So the y-intercept that's when x is equal to 0. So when x is 0, what is y? Well, y is also 0. So I already have an intercept 0, 0. So I know I have 0, 0 as an intercept. Okay. And then since we have the y-intercepts, we may as well find the x ones. This is a parabola, so it can have 2 intercepts. So let's see, be helpful if I spelled it right. So that's when y is equal to 0. So when y is equal to 0, I get x minus x squared. So what values do I get for x?
Wouldn't that be just 0 and 0?
Okay, 0, 0 is one of them, but there's one more.
Is it 1?
It is. Who said it was 1?
Lawrence.
How did you find 1?
I just did -1 to the power of 2, and then 1 minus 1
Oh, so you kind
be
of
0.
guessed a little bit.
Yes.
Okay, so you did trial and error. That's good. Trial and error works. I can take and factor out an x and get 1 minus x. And so now I see either x is 0 or 1 minus x is 0. So if x is 0, we already said y is 0. So we found that point. And if 1 minus x is 0, that says x is 1. And if x is 1, then y, believe it or not, is also 0. So we get the point 1, 0. So now I have this point. And I know that my parabola goes through that point and it can't be going up, so it has to go down. So therefore, the region that it's talking about looks like this. Okay, so we can use all of that to help us find our curve. So now what I want you to do is I want you to complete the problem. Okay, so I want you to complete the problem. So I'll give you a few minutes to work on that. Okay, is there anyone who thinks they have already set up the problem and would like to share? Again, we are trying to learn this material. Can anybody give me the formula that we're going to use?
Are you referring to the integral of y equals x minus x squared?
Well, we're not just integrating y. We're not just integrating y. We have to revolve this thing about the x-axis, and then that is going to give us an integral for volume.
Well, if that's the case, then we can draw the reflection of this, and then that would be -x plus x squared.
Okay, so we're going to draw the reflection of this down here. Good. All right, so now I've drawn the reflection, and I'm going to take a point. I'm going to locate it. I'm going to revolve it. So that's what I get. And when I do that, what structure do I see?
Like a sphere, a circle.
Okay, it's actually a disc. It is a circle. We see a disc. So there is my disc. So what method am I using? In order to create this volume, I am going to use the disc method. And what is the formula for the disc method?
Is it P times R to the second? Like,
Okay, so that's the area of a single disc. Good. So that is the area of a single disc. It is pi times the radius squared. Okay, so here I have a disc, and then I will draw its radius. So the area of this disc is indeed times pi times the radius squared. So that is what is going to go in here, the integral from a to b of pi times r of x, whoops. squared dx. Okay, so now you need to tell me what the radius is.
That would be our f of x, like our function.
Okay, so for this one, the radius, as exactly as you say. So if I go here and draw my radius in, it's in green. So if I draw my radius in, that means that the height at any given time is on the circle, on this curve. So since the height is on this curve, the height at any x is always equal to x minus x squared. So that is my radius. So r of x is x minus x squared. Okay. So now I get the integral of pi. My radius is x minus x squared, but it has to be squared. And what are my limits of integration? Where do I start and where do I end?
Is it from 0 to 1?
Okay, I'm going to start at 0 and I'm going to end at 1. So please note that this green line can start as far as 0 as a radius, and it can make its way all the way over to 1. Okay, so that is my region. All right, so now this is simple. This is just the integral from 0 to 1. I'll put my pi out here. This becomes x squared minus 2x cubed plus x to the 4th dx. So that's pi, and now I integrate. So I'm going to get 1/3 x cubed minus 1/2 x to the 4th plus 1/5 x to the 5th, evaluated between 0 and 1. Okay, any questions about that? Everybody see that? Now I wonder if this will do that. I'm not even going to attempt it. I'm going to do it myself.
So we're always taking antiderivative, Dr. Lott?
You have to. That's what the integral stands for.
Okay.
That sign right here, this right here says take the antiderivative and evaluate it between 0 and 1. That is the fundamental theorem of calculus. So I get
Yeah.
1/3 minus 1/2 plus 1/5. And that is equal to 1/30. Okay. Any questions?
I'm just wondering how where's you get the 1/3 half x, 1/5 x. I'm just curious how was that acquired?
Okay, so you're talking about going from here to here. Is that what you mean?
Yes.
Okay, so I integrated x squared. So again, I'm still using x to the n. The integral of that dx goes to x to the n plus 1 divided by n plus 1. And if it's no limits, it'll be plus c. So therefore, the integral of x squared dx says x to the 3rd over 3. So that's where I get this piece. And then I have the integral of 2x cubed. So that's 2 times x to the 4th over 4 plus c. And so that's how I get the 1/2. And then the integral of x to the 4th dx gives me 1 over 5 x to the 5th. And that is how I get that guy. So those were the most general antiderivatives. And then I evaluated them between 0 and 1.
One quick other thing. So based on looking at this, 1/5 x to the 5th is the same thing as x to the 5 over 5.
Yes, it is. Yes, it is. Because x to the 5 over 5 is basically, if I have 1 over x to the, like this is in the denominator. So put that over 1. So you get x to the 5th over 5.
I
Okay.
was wondering if you could evaluate the 1 over 0.
Oh, okay. So what happened to that? Okay. So this became pi times 1/3 1 cubed, which is 1, minus 1/2 times 1 to the 4th, which is 1, plus 1/5 times 1 to the 5th, which is 1, minus 1/3 times 0, minus 1/2 times 0, this is 0 cubed, 0 to the 4th power, plus 1 over 5 times 0 to the 5th. And so everything evaluated at 0 is gone. Okay. Question?
Is it just 1 over 30 the answer? Because we still have
Yes.
left the pi.
So, oh, I forgot the pi. Where's the pi? There's a pi. Thank you. There's a pi over 30. Thank you. That I did throw away my pi. Okay, this one's a little tougher. Okay, so we are trying to find the volume of the solid generated by revolving. So again, we're revolving a region about the line x equals 1. So that's what we're going to revolve it. The region is bounded by the curve x minus 1 squared equals 20 minus 4y, and the line x equals 1, y equals 1, and y equals 3 to the right of 1. Okay. So the line of revolution, we're not revolving this thing about x equals 0, the x-axis. The line of revolution is the line x equals 1 now. Okay, so whatever this thing looks like, so this problem that we just did, we were revolving about the x-axis. And so therefore it was a dx problem. Okay. Well, this one, whatever we graph this thing. We're revolving it about the line x equals 1. So x equals 1. So we're revolving it about this line. So that already tells me I have a dy problem. So whenever I'm revolving it about the x-axis or a horizontal line, I have a dx problem. But if I'm revolving it about the line x equals 1, with anything that's parallel to the y-axis, it's a dy problem. So therefore, I already know that my volume is going to be the integral from c to d of pi. And this time I need to write my radius as a function of y, dy. So I have to write the radius as a function of y. Okay,
Dr. La,
yes,
yeah, you forgot the square part before the dy.
thank you. Okay. All righty. So now what we need to do is we need to graph this thing. All right. So right now I have x squared, x minus 1 squared is equal to 20 minus 4y. Okay. So what does that look like?
Would it be a parabola?
It is a parabola. Okay, good. So this is another parabola. If you saw it like this, if you saw it as y was equal to ax squared plus bx plus c, you know right away it's a parabola. But the fact in here that I'm going to get an x squared when I multiply this out lets me know that I am getting a parabola. Okay, so let's do what we did before. Okay, so first off, when x is equal to 1, what is y?
Y is 0.
Let's see here. When x is 1, I get x minus 1. So I get 1 minus 1 squared is equal to 20 minus 4y. So that says 0 is equal to 20 minus 4y. So I get 20 over 4 is equal to y. So that's 5. So I do know that when x is equal to 1, the 0.15 is on the curve. Okay.
That'd be -5.
No. Because the 4y comes to the other side and then I divide by it.
Oh, okay.
No problem. Okay. So I know the 0.15 is on the curve. And then what happens if y is equal to 0? This is another parabola that is upside down. If y is equal to 0, I get x minus 1 squared is equal to 20. Okay? Doesn't help me a whole lot because x minus 1 is now the positive or negative square root of 20. So my x-intercepts are plus or minus 1 plus or minus the square root of 20. Okay, so the question is, where is that? So this is a problem that is not very easy to graph. We could put it into something that we would graph. Luckily, I have graphed it already, so I can know what it looked like. So when I graphed it, I got this parabola. Let me see here. Dun, 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 dun. Okay, go back 6.1. Okay, so my picture of this thing, it's an upside down parabola. And it looks like this. So far what we have is pretty good. It's up here, so it kind of looks like this. Who cares what it does up here? Okay, so it goes down like that. Okay, so it's actually kind of looks pretty bad, but that's not the best parabola ever. That looks a little better. Okay, when x is 0, when x is 0. Okay, so now it goes through the line y equals 3. So it says y equals 1. So let's draw y equals 1. And y equals 3. Okay, so there we go. So kind of difficult to draw, but we got it. So the region is bounded by this curve right here. So here's the curve, x minus 1. I want that black. Okay. It's this curve, x minus 1 squared is equal to 20 minus 4y. So that's the curve. This is the line x equals 1, y equals 1, and y equals 3. So I now see my region. So my region is this area right here. So that's my region. And I want to revolve that about the x equals 1. So when I revolve it about x equals 1, I'm going to get something on the other side that looks like that. And so I'm going to choose a value here, start on the curve, and revolve that thing. And there's my disk. So now I have the disk method. I already knew that. So now I just need to find my radius. So the radius of the disk is right here. So there is the radius of my disk. Okay. So now here is the difficult part. I need to give that a formula. I need to give that a formula. Okay, so this, remember, this is the axis here. So this is when x is equal to 0. Okay. So I need to figure out how long that is. Well, I know if I go start here and go all the way across. Come on now, do what I want you to do. That distance for any value of y, that distance is x of y. So whatever x defines by y. And then the distance from here all the way up to here is 1. So that distance is 1. So therefore, if I take the green distance and subtract the blue distance, I will only have the little black line. Does everybody see that?
Yes.
Okay, I see
I will.
Gustavo shaking his head. Anybody
Yes,
not
I
see
see
it?
that.
Okay, good.
I got
Okay,
a question.
okay, yes.
So you're telling me, so you're subtracting what you have for the green line by the blue line to get the black line.
Yes.
So, okay, I'm gonna see. Go ahead, continue.
Okay, maybe, okay, so you might not see it because I didn't draw it exactly there. So
I
let
mean,
me,
I see it. It just looks like the green and the blue are the exact same value.
no, 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 not at all. Okay, so watch the green line. Okay, so here is the green line. The green line starts here and goes all the way up to this curve, right? And then why don't we use pink? And then the pink line goes from here all the way up to there. So if I take the green and subtract the pink, that only leaves the black.
Mm. Okay, Professor.
You don't see it?
I gotta see you do this. I gotta see you do this.
Okay. No, you're gonna see this. I take this green line and I have a pink line. And if I say, if I take the green line and I subtract the amount of the pink line, then that only leaves that little piece.
Okay. Okay, that makes sense. Okay.
Ah, I told you, I said you was gonna get this thing. Okay, so now, because what I need is the length of the black line, because the length of the black line is the radius of my disc. So I need to know what the radius of my disc is. That's what the R of Y is. So the fact that it is R of Y, now this is where it gets tricky. The fact that it is R of Y means it has to be a function of Y. So that means I need to solve for this curve in terms of X. Stop. Okay, so I have, in terms of Y, I have X minus, so I have X minus Y squared is equal to 20 minus 4Y. So now if I take the square root of it, I get X minus 1 is the square root of 20 minus 4Y. And if I add 1 to it, I get X is the square root of 20 minus 4Y plus 1. Now you should be saying, how come you didn't do plus or minus? Well, the reason why I didn't do plus or minus is because I know it is on, all the X's are positive. See, I'm on the right side of the axis, right side, so all the X's are positive. So I don't want the negative part, I only want the positive part. So even though this is truly plus or minus, I only want the positive part. Okay, so now that X, so it doesn't, so whatever Y you give me, so if you give me this Y, I can tell you what that value of X is on the curve. If you tell me this Y, I can tell you what that value of X is. If you give me this Y, I can tell you what that value of X is, because I just told you a formula that says, depending on the Y you give me, I now know what X is. So therefore, this distance is this formula, which is, so now I can find my radius. So R of Y says take the square root of 20 minus 4Y minus 1. That's this curve. And subtract off X equals 1. That is that curve, and it will always give me the piece in between. So that's my radius. And this is plus 1. That's my radius. So now R of Y, how nice is that, that the plus 1 and the minus 1 drop out. They knew not to revolve this thing about the 0 axis because it would have been awful. So now my volume is the integral of pi. And now I'm going to get the square root of 20 minus 4y. And that thing gets squared dy. So what is missing?
I believe the part that is missing is the boundaries.
Good, the limits of integration. So now this is how you figure it out. Where does that black line start?
X equals 1.
Okay, that's where it starts. Okay, so good, good, okay. But this is a Y problem. So that black line is moving up. In order for me to get every piece of this region.
Oh, so it starts at ooh.
That's the black line. It's on your tongue, just say it.
Is that
Look at the picture. Look at the boundaries on the thing.
Is it 1 and 3?
Okay, who said 1 and 3? Gustavo?
No,
No, somebody else was unmuted. Who said 1 and 3?
me.
Okay. Oh, I see you. Okay, I got you. Okay. When I'm looking at my screen, I can only see 4 students at a time. So I kind of try to go with who was unmuted. And so that's why I got it wrong. I see De'Ara is unmuted too. Okay, so De'Ara,
yes.
that black line, you see this black line starts way down here at y equals 1.
Mm.
So this is that line, y equals 1. I don't know why my thing is having a problem today. And it goes all the way up to this line, y equals 3. So that black line can start down at the bottom and it goes all the way up at the top. And it's stuck between x equals 1 and this curve.
Okay.
So it starts down there at y equals 1, and then it gets stacked up like a deck of cards until it gets all the way to the top. So it goes from 1 to 3. So this is now pi times the integral from 1 to 3. What's inside just becomes 20 minus 4y dy. So now I get pi. I'm going to get 20y minus 2y squared, evaluated between 1 and 3. So now I get pi. I'm going to get 20 times 3 minus 2 times 9. So that's the first piece. And then I'm going to subtract off 20 times 1 minus 2 times 1. Okay. So that's pi. 20, so I'm going to get 60 minus 18 minus 20 plus 2. Does that look right? That's what it looks like to me. This is 24 pi. So when you are doing these volumes by revolution for the disk method, you will have something. So the easy ones, the easier ones will give you a region like this. This is y is equal to some f of x. And so then you will revolve it down here like this. You will find your point, and do that, and get a disk. Find the radius of the disk. Call that radius. This is the easier ones. So the radius r of x will just be whatever your y is, or your f of x. You'll know that this point right here will be your A, and this point will be your B, and then your volume will be the integral from A to B of pi times r of x squared dx. Your more difficult ones would be something like this. So your more difficult ones would be something like this is like y is equal to, let's say 5. And then you have something that looks like this. And so this right here is my y, is my f of x. And so I would find this value right here would be A, and this value right here would be B. And now my radius is to take this whole thing, starting here and go all the way down, and then subtract this piece. So then I would subtract this piece, And then that will give me my radius to be this piece. So for something like this now, my radius would be to take the top function f of x and to subtract the bottom function, which might be 5. So now I would get the volume would be the integral from a to b still. I still go from where it hits there, not where it hits the x-axis, but where it stops. And then I would have pi. And now my radius is going to be f of x minus 5 squared dx. And that's if I'm revolving it about this axis, about this point. So I would have something like that. Okay, tomorrow we're going to finish this section. We are going to do volumes by washers, and that'll be it for this section.